Probability theory is going to provide us with the foundations that we need to develop mathematical models for chance phenomena and actually to analyse data scientifically. Now we're talking here about chance phenomena or randomness, and the reason why we're interested in randomness is that random variation characterises many of the phenomena that we observe and study in the real world. And that random variation might arise from measurement procedures. So it may be phenomena are difficult to measure, and for that reason our measurements are inexact or imprecise, and they tend to vary from sample to sample. Or it may be that the phenomena themselves are simply characterised by natural variation. So for instance, the birth weight of children is not deterministic, it's random. The height of oak trees is not deterministic, it varies. Now, the implication of random variation is that there's a degree of uncertainty and variability in the scientific analysis that we conduct on those phenomena. And the key goal of probability and ultimately of statistical modelling is to establish a mathematical framework within which the randomness can be quantified so that systematic variation can be studied. So that's what probability is all about, random variation. Now, we understand probability intuitively. We understand it in the decisions and actions we take in our daily life. So when we travel to college for a lecture, we don't know exactly how long it's going to take us to get to college. We may be a bit early, we could be a bit late. When we go in to sit an exam later this year, we don't know the exact result we're going to get in the exam. So there's a degree of randomness and uncertainty surrounding that. That's intuitive probability. But the point about probability theory is we want to establish a formal mathematical treatment that lets us represent uncertainty systematically and ultimately lets us carry out scientific analysis of random phenomena. So that's what we're looking at. And in this lecture, we're going to outline key concepts and foundations that will let us draw a probability model. So we want to model or compute the chance of observing phenomena. To do so, a probability model is what we're going to need, and it's going to draw on a number of concepts and definitions that we're going to bring together and define some key aspects of probability. So, a probability model. First three elements that I want to draw your attention to are on this slide. First, we're talking about experiments in the statistical language. Now, an experiment in statistical language isn't actually a scientific experiment. It's any one-off or repeatable process that we can conduct that fulfills two criterion. There is a well-defined set of possible outcomes for the experiment, but the actual outcome of the experiment is not known in advance. So for instance, the two examples I gave in the previous slide, travelling to college, is an experiment. We've got a well-defined set of possible outcomes measured in time, but we don't know how long it's actually going to take us to get there, so we don't know the actual outcome. We go into an exam, that is an experiment. There's a well-defined set of possible outcomes ranging from 0 to 100%, but we do not know the actual outcome in advance. So that's an experiment in the broadest sense. We've talked about outcomes, two further definitions on outcomes. A sample outcome, small omega, is one possible outcome of the experiment. 100% in the exam, 50% or 60%, that's three sample outcomes. The sample space is the set of all possible outcomes of the experiment. Okay, so in the case of the exam mark, it's the integers 0 to 100, or it could be some subdivision of those integers. But that's the sample space, the collection of all possible outcomes. And in statistics, depending on the experiment, the sample space could be finite. It could be, so finite, it has k elements, whatever the number k is. It could be infinite with an infinite number of elements, or it could form some interval of real space as given by that expression there. So that's a quick definition of experiments, sample outcomes and sample space. Next I want to introduce the concept of an event. An event is simply a designated collection or set of sample outcomes. An event E occurs if the actual outcome of the experiment is within that set. So it's just a set of sample outcomes. It could be a single outcome, or it could be a set containing more than one element. Two special cases of events are as follows. The event corresponding to the set of all sample outcomes, that is big omega, the sample space, is the certain event. And the event corresponding to a collection of none of the sample outcomes, the null set, is the impossible event. And notice that we're using the word set. Events are sets in a mathematical sense, and for that reason, set theory, algebra and notation carries over. I'll briefly review this here. I know that all of you will be familiar with this, so we'll go through this quickly. But the algebra of set theory carries over directly into probability. So for two events E and F in the sample space, these two sets, the three basic operations that we're going to talk about are union, denoted by the this symbol here, E union F. That means that both E or F or both occur. Intersection, E intersection F, both E and F occur. And complement, we denote this by putting a prime on the event E, and that means that the event E does not occur. That's the complement of E. So if we take three events in the sample space, E, F and G, the properties of set operations that we're going to use, and that most of you will be familiar with, are simply that they're commutative. That is, the order of operations makes no difference. So the union of E, E union F is the same as F union E. E intersection F is the same as F intersection E. The operations are associative. That is, rearranging parenthesis does not change the result. So E, the union of E and open brackets F union G is the same as open brackets E union F close brackets union G. Same for intersection. The operations are distributive. What this simply means is that union distributes over intersection and intersection distributes over union. And finally, we have laws relating to the complements of set that are called De Morgan's laws. So the complement of the union of E and F is equal to the intersection of the complements of E and F. And those laws are very straightforward, and actually in your own time perhaps draw some Venn diagrams just to confirm that you're happy with them. Okay, so experiments, events and outcomes. We've talked about them in theory. Let's just look at some concrete examples. So first, we have 5 experiments here. The first is coin tossing. So we're tossing a coin. This is an experiment. The sample space has 2 elements. The experiment can either have one at the outcome heads or it can have the outcome tails. We throw a dice. What's the sample space? The sample space is the events 1, 2, 3, 4, 5 and 6. So simply these 6 integers comprise the sample space. We could have an experiment that involves proportions. In this case, the sample space is a number that varies between 0 and 1. So for instance, the mark in an exam, if we express it not as a percentage but as a proportion, that would be an experiment that has this kind of sample space. So 0 corresponding to a failure where no questions are answered correctly, and 1 corresponding to an outcome in which every answer was correctly delivered. We could have an experiment in time measurement. All I'm trying to point out here is how sample space differs depending on the type of experiment. In this case, with time measurement, the sample space is a positive number on the real line, so the positive part of the real line. How long is this lecture going to last? We don't know. It's an experiment with an uncertain outcome, and that's the sample space of this experiment. Temperature measurement and so on, lying in a range, but I hope that you get the message here. So the sample space of A and B is finite. The sample space of C and E is an interval on the real line, and the sample space of D is potentially infinite, the way we've expressed it there. Important distinction. Experiments A and B have discrete outcomes. They can be written in integer form. This could be, we could replace H and T by 2 integers, 0 and 1, commonly done. This is a set of integers as the outcome. C, D and E have continuous outcomes, all of them defined somewhere on the real line. Discrete outcomes correspond to an experiment that involves counting. Continuous outcomes correspond to an experiment that involves measurement. Okay, so experiments, events and outcomes, and I now want to talk about the probability of those events. So for any event E in the sample space, the probability that E occurs is written in this form here, P open brackets, E close brackets. And this probability operator, or what's called the probability function, is a set function that assigns weight to collections of the possible outcomes of an experiment. You can think of probability essentially as being a measure of the likelihood of an event occurring. And the probability function is governed by a set of axioms that let us then go on to develop the calculus of probabilities and deal with probability mathematically. And there are three key axioms of the probability function. First, let E be an element of the sample space, then the probability that E occurs is a number that lies in the closed interval between 0 and 1. So a probability equal to 0 means that E cannot happen. A probability equal to 1 means that E must happen. And anywhere between this line measures the degree, the likelihood of E occurring. Okay? And as that probability gets larger, the likelihood is increasing. Second axiom, the probability of the entire sample space equals 1. Now that may seem obvious, but it's an important axiom. What it's saying is at least one event in S in the sample space, omega, will occur. So if we toss a coin, the probability of heads is 0.5, the probability of tails is 0.5, but the probability of throwing heads or tails has got to be 1. One of those events has to be an outcome of that experiment. So the probability of the sample space is always 1, and that's quite useful to make certain calculations. Okay, if we have two events E and F in the sample space, and if those events, or the intersection of those events, is the null set, that is, these two events cannot occur together, then the probability of E or F happening is the sum of the two probabilities. So if we throw a dice, it's not possible for the dice to have the numbers 1 and 2. That's a null set. The dice can take the number 1 as an outcome, it can take the number 2, but it can't take both. So the probability of it being 1 or 2 is equal to 1 over 6 plus 1 over 6 equals 1 over 3. Now, some results follow immediately from these axioms that are going to be useful in developing probability theory, and these are as follows. First of all, the probability of the complement of E is equal to 1 minus the probability of E. This must follow from axioms 2 and 3. The probability of the sample space has to equal 1, and we have this addition here. So these are mutually exclusive events. Probability of E complement must be equal to 1 minus the probability of E. The probability of the null event must equal 0. That follows from axioms 2 and 3 directly as well. Just in exactly the same argument can be applied to this. If E is a subset or equal to F, then the probability of E must be at least as large as the probability of F. That follows directly from axiom 3, from this addition, that must be true. And in general, the probability of E or F occurring is equal to the probability of E plus the probability of F minus the probability of the intersection of E and F. So what we've done here is we've taken axiom 3 and we've generalized it a bit. We've said we're not going to enforce the condition that E and F, the event E intersection F is the null set. We're going to allow that event to happen. But if we were to draw the circles in a Venn diagram, probability of E and the probability of F, we have to subtract off this intersection, otherwise we double count it by just adding E and F together. And again, in your own time, try and draw those Venn diagrams so that that's clear. Now we can take this result that we've just discussed a little bit further in the axioms of probability when we talk about disjoint events. So two events E and F are said to be disjoint or mutually exclusive if they can't occur together. So if they have a null, if the intersection is the null event. We can also talk about any number of events as being pairwise disjoint or mutually exclusive if all of the pairs have a null intersection for all I, and j. So all that pairwise disjoint is saying is that any pair of events has an anti-intersection. That's all it's saying. Now disjoint sets are therefore sets that have no point in common, of course, because they have this null intersection. So if we draw a Venn diagram of two disjoint sets, the sets do not overlap. So if events E1 to EK are pairwise mutually exclusive, then by the result we have here, by axiom 3, it must be the case that the probability of the union of those events is equal to the sum of the marginal probabilities of those events. So just an important note here, we often deal, so that all this is doing is extending axiom 3 to the case in which we have k rather than just two events, we've got k events. Now, we often deal with probabilities of single events and probabilities for intersection events, and for convenience we're going to use the following terminology. When we refer to the probability of an event itself, P open brackets E, that's the marginal probability of E, marginal. When we refer to the probability of an intersection, E intersection F, we're going to refer to that as the joint probability of E and F occurring. Now, there's an important relationship between joint and marginal probabilities that we're going to use to talk about the next concept in probability, conditional probability. And this is concerned, or conditional probability, is concerned with the probability that a particular event occurs given the occurrence of another possibly related event. So, again, define two events E and F in the sample space. The conditional probability that F occurs given that E has occurred is written probability F, vertical line E, and it's defined as the ratio of the joint probability of E and F to the marginal probability of E, as long as the marginal probability of E is positive. So let's give an example of conditional probability and try and explain a bit about what it means. So we have a standard playing deck of cards with 52 cards, and a card is drawn from that pack. Now, the marginal probability of that card taking any of the 52 values is of course 1 over 52. But in conditional probability, we're not interested just in the marginal probability. We're talking about the probability of an event given and another event has occurred. So let's say we're told that the card is an ace. What is the probability that the card is the ace of diamonds given that it's an ace? Now, you know immediately what that probability is, but let's just go through the algebra here so that we can work it out from the formula for conditional probability. Now, the probability of drawing an ace is 4 over 52 because there's 4 aces in the pack, which means it's 1 over 13. That's our marginal probability of drawing an ace here. Probability of ace of diamonds given ace equals divided, the denominator is the probability of drawing an ace. The probability of drawing an ace given that it's an ace, sorry, the probability of drawing an ace of diamonds given that it's an ace, the numerator, is simply the probability of the ace of diamonds, because of course the ace of diamonds has to be an ace, so that's 1 over 52. So to calculate our conditional productivity, conditional probability, we divide 1 over 52, this expression, by 1 over 13, this expression, and it gives us 1 over 4, or 0.25. So what does conditional probability do? Well, by conditioning, we narrow the sample space. In this case, we had 52 cards, but once we know that we're conditioning on the card already having been an ace, then we're actually down to just 4 cards because there's only 4 aces in the pack. That's why the probability ends up being 1 over 4. So conditioning narrows the sample space. And so we now have this relationship between joint probability, marginal probability, and conditional probability, and we can play around with that and express each of these terms in a different way, as you can see. So, from the definition of conditional probability, we can write the joint probability as the product of the marginal probability of E times the probability of F given E, the conditional. Marginal times conditional. This leads us to an important observation, that if two events E and F are independent, then the probability of F given E is simply the marginal probability of F So if two events are independent, conditioning on E adds no extra information. It doesn't narrow the sample space. It doesn't narrow the sample space. So in that case, the joint probability can be expressed as the probability of E times the probability of F. So let's give an example of that. We have two experiments. One is we throw a dice once and we want to know the probability of it taking the value 1. And in our second experiment, we simply throw the dice again and we want to know the probability of it taking the value 1. Now those two events are independent. The second throw of the dice has got nothing to do with the first, and the first has got nothing to do with the second. So in that case, the probability of event E, dice taking 1 on the first throw, and the dice taking the value 1 on the second throw is just the product of the probabilities. 1 over 6 times 1 over 6 equals 1 over 36. But if events aren't independent, this is the expression we use for the joint probability. And that's just when we've got two events, but we can generalize this up to k events, and it just gets written out like this. And again, in your own time, just make sure you're happy with this. It's exactly the same process, but just written out for k rather than two events. And this result, these two results here, this one and this one, is known as the chain or multiplication rule. And it's actually the mathematical representation of a probability tree, which we'll look at in the next slide. So in a probability tree, we have nodes. This is the first node, this is the second, two nodes here, and we have four nodes here. This first node is actually the certain event. So this is just the entire sample space. These two nodes represent the first partition of the sample space into two mutually exclusive events, E and E complement. And these nodes here represent the second partition of the sample space into four events, F given E, F complement given E, F given E complement, F complement giving E. So you can see it branching out. These have to be conditioned on E complement having happened. These are conditioned on E having happened. And then if we simply use the formula that we looked at in the previous slide, these formulas here for joint probability, we can calculate the joint probability at any point in the tree by multiplying through in these ways. So the joint probability of E and F happening is the probability of E times the probability of F given E. The joint probability of E and F complement is the probability of E times the probability of F complement given E. And there's a simple example given here of a two-step coin toss. So we're interested in working out the probability of obtaining heads in the first toss and heads in the second toss. And from this equation here, we can see that that's equal to the probability of obtaining heads in the first toss times the probability of obtaining heads in the second toss, given we obtain heads in the first toss. Next one, we won't go through this in all of them, but the probability of obtaining heads in the first toss and tails in the second toss is probability of obtaining heads, this event here, say, times the probability of obtaining tails, given we obtain heads in the first toss. So that's how a probability tree works, and that's how the calculation of joint probabilities follows. Notice in this particular case that these conditional probabilities actually reduce to marginal probabilities because the two steps in the coin toss are independent, and so we end up with these numbers that are very uniform and exactly the same. That's only because we've used a fair coin. In another example, that might not be the case. But again, look at this in your own time and make sure you're happy with how you can follow down the branches of these trees to reach these computations. Okay, I now want to turn to the theorem of total probability. And again, this is a relation between conditional and marginal probabilities. And it's useful because we might want to calculate the probability of an event using conditional and marginal probabilities that arise from some partition of that event. Okay, I'm going to give an example in a second where we do that. Just to define what we mean by a partition, a collection of events E1 to EK is said to partition some other event F if the sets are mutually disjoint, so these events are mutually disjoint, and the union of these events gives us F. That partitions it. That's what a partition is. So if E1 to Ek is a partition of F, then the theorem of total probability says that the probability of F happening is equal to the sum of the conditional probability of F given each element of the partition times the marginal probability of each element of the partition. And that simply follows actually from axiom 3 of probability rules. And there's a little proof here that, again, go through it in your own time and make sure you're happy. But if E1 to Ek form a partition of F, then we can write F definitionally as the union of the intersections of F and each element of the partition. Then we can take the probability of this expression, which by axiom 3 must equal the sum of these intersections. That's what axiom 3 tells us. But by the definition of conditional probability, we can replace these terms by the probability of the conditional probability times the marginal, as we've just seen conditional probability, and that gives us our theorem of total probability. So the probability of an event being decomposed into these elements of its partition. So let's take a concrete example. What's the probability of being on time for a lecture? So a student is travelling to the lecture using either train or bus. We don't know what the probability of them being on time is, but we do know the following probabilities. We know that the probability of being on time by train is 0.9. We know that the probability of being on time by bus is 0.8. And we know that the probability of them travelling by train is 0.6. And the probability of travelling by bus is 0.4. So by the law of total probability, we can calculate the overall probability of being on time by lectures by simply using the expression we saw in the previous slide, which gives us 0.9 times 0.06, 0.8 times plus 0.8 times 0.04, or 0.86. So the way to look at total probability is that we're computing an average, this overall average, by weighting each conditional probability by the probability of having to condition on that event. Okay, that's really what this is telling us. Okay, and finally, in this section of the lecture on the foundations of probability theory, I want to talk about Bayes' theorem, which is a specific representation of conditional probabilities. It's very, very important in a branch of statistics known as Bayesian inference, and generally it's a key result in probability theory. And what Bayes' theorem says, we'll state it first, is it says for any two events in the sample space with positive probabilities, then we can write the probability of E given F in this form here. The probability of E given F is equal to the conditional probability of F given E times the marginal probability of E divided by the marginal probability of F. Now, we saw a definition for conditional probability earlier, and it hasn't changed. All we've done is we've replaced the probability or the joint probability of E and F with this expression here. And notice that this is the probability of E given F, but on this numerator we have the probability of F given E, and that is what Bayes' theorem does. By the conditional probability definition, we can write the joint probability of E and F in one of two ways. We can write it as the probability of F given E times the probability of E, or we can write it as the probability of E given F times the probability of F. And what Bayes' theorem does is it uses this reversal to draw inference about this conditional probability from that conditional probability. And that is very important because in general those two conditional probabilities are not the same, and it's crucial to condition on the correct event in a conditional probability calculation. So Bayes' theorem is important. It's important for all sorts of reasons, but not least because it allows us to compute a potentially unknown conditional probability from one that we do know, and vice versa. And let's look at a specific example. In this example, we're concerned with diagnostic testing for COVID-19, and the diagnostic test that we're looking at is claimed to have 95% sensitivity, so 95% of people who have COVID, who actually have COVID, will test positive. It's got 98% specificity, that is 98% of people who do not have COVID will test negative. Now, in the population, there's a COVID prevalence of 1 over 1,000, and what we want to know is, what is the chance that someone testing positive actually has COVID? That's a conditional probability. What's the probability that they have COVID given that they've tested positive? And we don't know that conditional probability, but we're going to work it out from the information that we do have. So let D be the event that the individual is truly COVID positive, and let T be the event that they test positive on the test. Well, we know from the claims of the test that they will test positive given that they have COVID 95% of the time, so that probability is 0.95, and they will test negative if they don't have COVID 98% of the time, so that probability is 0.98. And the probability of them having COVID in the first place is just the incidence in the population, which is 1 over 1,000, or a probability of 0.001. Now we want to know something specific. We want to know what is the chance, what's the probability that someone actually has COVID when they've tested positive. And using Bayes' theorem, we can work this out from the information that we have. And the solution is given as follows. This is the equation we've just seen. We're going to break down the probability of T using total probability. So we're going to express this denominator as we did do a couple of slides ago. We're going to express this using total probability in terms of conditionals and marginals. And that's, we're going to use the numbers in the previous slide. This is how we write it out. Okay, conditional probability times marginal, conditional times marginal plus conditional times marginal. And that gives us a number of 0.045. So the result we get actually is that over 95% of those testing positive will in fact not be COVID positive. So we've been able to compute a probability we didn't know using Bayes' theorem. Now note that the disease prevalence figure can be thought of as what's called a prior probability. This is a key concept in Bayesian inference, prior probability, and it indicates what we believe about the presence of the disease a priori, and in this case we believe it's unlikely because it had an incidence of 1 over 1,000. Using Bayes' theorem, we've been able to calculate how a test result changes our belief that a person is COVID positive. And as I said, Bayes' theorem is going to be crucial to us at other parts in the course. Okay, that concludes this very concise introduction to probability theory. In the next part of the lecture, we're going to go on to use probability to talk about random variables.